Hey guys, welcome back. So today what we're going to be looking at is we're going to start looking at the Unit 4 stuff. So if you just quickly have a look at the front of your textbook chapters, it actually tells you which ones are the Unit 4 and the Unit 3 stuff. So your Unit 4 stuff starts Chapter 6 and then finishes Chapter 12. Okay, so this is all the stuff that is not going to be assessed this year in a Unit 4 specific exam. This will be assessed in your end of year external exams, however. And the external exams, I don't know what's written on those. So I will go through, I will upload videos for each chapter for you. I do also have the worked examples for this on the eLearn, but I think it's a lot easier to do a video for them than to do the worked examples. And I also think that I can get a lot more information across this way. So what I'm going to do, and we're going to start off with a nice simple example here of some integration. And we like to call this, or I've heard it being called, the reverse chain rule. And then I've also seen like the reverse product rule or the reverse quotient rule if you want to get super crazy. We're going to start off with a nice simple one. So typically when we are using the chain rule, let's just go back to differentiation for a second. This is what's called the reverse chain rule because we're integrating, not differentiating. If we had something like 5x take 9 to the power of 6 and we wanted to derive that function, then we would let the inside function equal to u, and then we would derive that to get du dx. And then we would rewrite the entire function with u, so then y is equal to u to the power of 6, and then we would find the derivative of y with respect to u, and that's going to give me 6u to the power of 5. Then I would use my chain rule. So my chain rule is dy dx is equal to du dx times by dy du. And by doing that effectively, algebraically, I'm cancelling out those two terms there to be left with dy dx. So I have 5 times by 6u to the power of 5. And then I would substitute that inside function back in to get 30, 5x take 9 to the power of 5. So what we're going to be doing today is we're actually going to be doing a reverse of that method. The first thing I did with that chain rule was I picked the inside function, and here's the thing, we're always going to pick this inside function. We're always going to let this inside function be equal to u. Sometimes we might have like extra variables and stuff on the outside. We're not going to worry about those. We're always going to let that inside function equal to u. Okay? So u is equal to 5x minus 9. And just like with the chain rule, we're going to find the derivative. So du dx is going to be equal to 5. Now this is called linear substitution because we're going to start substituting some values in. And what I want to do is I want to find what dx is equal to so I can substitute dx in here. So I'm just going to rearrange this to get this in form of dx. So this is going to be du over 5 is equal to dx. I could also write this as 1/5 du. Okay, so I can substitute that information in there now, and I can also substitute in u here. So this becomes the integral of 1 over 5 du, because with 1/5 we've just separated it out from the du, of u to the power of 6. So now this is going to be a really simple thing to find the integral of, because when we are finding the integral, we're just going to move this to the outside, this scalar value, and we're just going to use the normal rule that we always use. So we're going to add 1 to this power and then divide it by the new power, and that's going to give me 1/5 times by u to the power of 7 over 7. So now I'm just going to substitute that back in. So that's going to give me 1 over 35 times by 5x minus 9 to the power of 7. Really nice, really simple. I really like this method. Okay, let's do another example. So I'm going to move through this one a bit quicker. So we're going to let u equal to the inside function. We're always going to let u equal to the inside function. Then we're going to find the derivative of that function. Then we're going to rearrange. So I might write this as 1/3 du this time is equal to dx. And I'm going to substitute u for this inside function. I'm going to substitute 1/3 du for the dx. And this is going to give me the integral. I'm going to actually pop that 1/3 out the front there just to move it out the way. Excuse me. U to the power of 6 du. And this is a nice simple one now because we're just going to raise this to the power of 1, divide it by the new power. So this is going to give us 1/21, because 3 times by the new power of 7 is going to be 21. U to the power of 6, and then I'm just going to substitute in my inside function, 3x minus 5, 3x minus 5 to the power of 7 over 21. Plus c. We've always got to do plus c. I'm a maths teacher and I even forget this stuff, so I do apologize. So we always have to add that plus c on the end there. So some nice simple examples of some integration by linear substitution using the reverse chain rule. So what happens now when we have a more complex example? So I'm just going to just having a look at your textbook here, just going to have a look at a little bit more of a tricky example. And I'm just going to scroll down. All right, so I've picked myself a nice tricky one. I do like the tricky ones. And what I'm going to do is I'm going to rewrite that square root function using x minus 1 to the power of a half. And now I can see that I'm going to be able to let this inside function here be equal to u. And then we're going to do the exact same process. So u is equal to x take 1, du dx is just going to be equal to 1. I'm going to rearrange this so that I get dx is equal to something. So what I'm going to do, this is a nice easy one, du is actually equal to dx, so I'll be able to substitute this in straight away. Now, this is where it gets a little bit tricky because we have this other variable x here. So if I was just to rewrite what I've done, I would have x multiplied by u to the power of a half du, and I would still have this x to deal with. And I can't integrate with respect to u when I've still got this variable x that's involved. And so what I'm going to do is I'm actually going to try and write this in terms of u by using this equation here. And I can do that by writing u plus 1 is equal to x. So now I can substitute that into that equation there. So I have u plus 1 times by u to the power of a half du. So now it's going to be a little bit easier for me to integrate with respect to u. So to do that, we can't really expand the brackets out here because this is u to the power of a half. So what I end up with, if I do u to the power of 1 times by u to the power of a half, that's going to give me u to the power of 3 over 2 plus u to the power of 1/2 du. Okay, so that's a little bit nicer now because these are pretty simple to integrate. So what I'm going to do is I'm going to add 1 to the power and I'm going to divide through by the new power. So u to the power of 3 over 2, adding 1 to that becomes 5 over 2. When you divide by 5 over 2, that's the same as multiplying by the reciprocal 2/5. So that's how I've gotten those solutions there. And that's the similar process there for u to the power of 3 over 2. Okay, so for this one, I haven't added the c, and that's because I put the square brackets around it. So that's a little tip. If you don't want to, or you forget to write the plus c at the end, I just put the square brackets around because when I put the square brackets around, that means I'm finding the area between two particular points, and therefore the c ends up being cancelled out. Okay, so now what we can do is we can write that initial function of u, which is x minus 1, back into that equation, and then we can substitute in our values for 1 and for 2. Okay, so when we write this, I'm just going to scroll down a little here. We're going to have this first part of the equation is always going to be from this top number. So now I'm going to use round brackets because we're actually performing an equation. We only use square brackets when we are doing integrals from a particular range. So this is going to be 2 lots of 2 minus 1 to the power of 5 over 2 plus 2 lots of 2 minus 1 to the power of 3 over 2 over 3 minus that exact same thing, except instead of the 2, it's going to be a 1 now. Again, I wouldn't write that plus c because I would have plus c in this part of the equation here, and I would have plus c in this part of the equation. C minus c is just going to cancel out, so there's no point even putting it in there. Okay, so let's go through and let's actually solve this value now. So this is going to be 1 to the power of 5 over 2. 1 to the power of anything, nice and simple, is going to be 1. So this is going to be 2/5 plus 2/3. Oops. minus, and this one's even easier because 1 minus 1 is 0, and so 0 to the power of anything is also 0. And so 2 times by 0 is 0. So this whole thing is just going to be minus 0. So this is a nice simple one too. Last thing I need to do is I just need to add my fractions. So I'm going to do that by cross multiplication and then making them into like fractions. So this will be 6 over 15 plus 10 over 15, which is going to give me 1 and 1 over 15. So those are just some more of the simple familiar type examples for integration by linear substitution, aka the reverse chain rule. It's a really nice one. I really like this. It's very algebraic. Alrighty guys, talk soon. See you later.